With no further ado, it's time for our third company already. Let's bring up OCO Corporation and CEO Todd Brix. OCO Corporation is doing something really hard, converting carbon dioxide generated by industrial and fossil fuel power plants into a value-added platform chemical known as formic acid. Let's hear more about this.
Thank you very much. Good afternoon, Bend. My name is Todd Brix. I am the CEO of OCO Corporation. We're an Oregon-based company. I myself was born and raised in Kennewick, Washington, just a few hundred miles up the road. OCO has a different solution to the problem of carbon dioxide because we think about carbon dioxide differently. We think about it as OCO, and we want to use, not waste, carbon dioxide. So we have 300 million problems for CO2 emissions in the United States today. They come out of a variety of different sources across all the different economic sectors of our economy: transportation, residential, gas stoves, gas furnaces, electricity generation, and industrial sources. The good news, though, about this is that half of the CO2 emissions only come from 3,000 plants. And each of these 3,000 plants are owned by large companies with large balance sheets, and each one of them is going to become a customer of OCO. So the problem is man has figured out a way to take carbon dioxide out of flue gas emissions. It's been around for 15 or 20 years. The problem is it's very expensive to do. It costs approximately $120 a ton to take carbon dioxide out of flue gas. And you can only sell that carbon dioxide for about $30 a ton, mostly going into the fizzy Coca-Cola belly wash industry or into enhanced oil recovery operations. So very few CEOs who want to keep that title for a long period of time are going to sign up for a value proposition like that. What we do, and our solution, takes that cost differential and more than makes up for it by turning it and converting it into something worth $1,000 a ton called formic acid. What is formic acid? Many of you may have taken your high school chemistry course and learned about a carboxylic acid. But formic acid, for the purposes of today, you need to understand that it's a billion-dollar market. And it's used in almost every single manufacturing, agricultural, consumer, and industrial type of use across the planet. From it being a natural animal feed preservative that's used in Europe, because they were able to get rid of all the antibiotics in their meat supply in the EU because they replaced it with formic acid as a preservative for feed silage, and many other types of products and applications. Formic acid is environmentally benign. In fact, our largest competitor for formic acid today is the ant. Ants make billions and billions of tons of formic acid every year as a natural bactericide. So do plants and stinging nettles. However, our commercial competitors produce in a little bit smaller quantities, and they make it in about 1 million tons per year today, and they make it from methane natural gas using fossil-based processes and fossil-based feedstocks. We want to replace that with the EC-form process. What the EC-form process is, it electrocatalytically converts carbon dioxide with water and lots of electricity, renewable electricity preferably, into formic acid. And we do that in a modular way via a whole series of electrochemical cells that are encompassed inside of a module. And that module is roughly the size of a relatively large refrigerator on its side, about 1 meter by 1 meter by 2 meters in size, which can be mass-produced and mass-manufactured at a very, very high scale volume and a very low cost. These are arranged inside of a manufacturing plant where we add separations technology. So there's 5 key innovations that OCO has pioneered and patented with 17 global patents that are exclusively licensed today. This has been known, the chemistry has been known since the 1880s, and people have banged their heads against this problem for 140 years until today, until OCO. We've done it with 5 things. 1, a highly selective catalyst. So what you see here presented is our OCO technical performance readout with those of the previous best results over the last 5 years of the leading researchers in Japan, Europe, and the United States who've looked specifically at converting carbon dioxide into formic acid. Our catalyst is more selective, and it's far cheaper. We use tin. Most everyone else uses rare earth metals like palladium or rubidium or ruthenium. And we have a long-lasting catalyst that lasts 2 years, not 2 months. We're a very efficient user of our renewable electricity resources, converting 76% of it into chemical bonds that are inherent inside the formic acid molecule. We operate at room temperature and room pressure, so we don't need or generate a lot of waste heat or a lot of co-products that aren't very useful or valuable. The really cool thing is that we can use intermittent electricity and shape-shift our production relative to when the sun shines or the wind blows. Because we're not hot, and because we're operating at ambient pressure, we can just turn our system on and off depending on the availability of renewable electricity. And last but not least, we use extractive distillation technologies that have been developed to separate easily formic acid from water as a co-product form. The net result of all these innovations is that we can make formic acid for about $430 a ton. The best that the rest of the world has come up with, from a published research perspective at least, is about $2,000 a ton. And this is really cool. That means we're 78% lower cost than the best results. And most importantly, and this has always been a challenge, and for anyone in the green chemical or renewable energy space, is that we are actually 30% less costly than fossil-based methods of production today. And we're only going to get better and better with our cost structure going down by 6 to 7% every year for the next 15 to 20 years, until which point formic acid will be the price of a gallon of gasoline. And that will change everything. Our road to commercialization started with a company called Det Norske Veritas, a Norwegian technology and risk management company who services almost every single oil and gas company on the planet, every maritime shipping company, every utility company on the planet. And they had a small R&D team in Ohio, and they were chartered for the last from 2008 to 2016 to come up with a technology that answers a simple question: how can we help our customers turn carbon dioxide into something profitable and not be a cost center? And the only answer they came up with after an extensive techno-economic analysis, laboratory experimentation, and a whole variety of scale-up steps was formic acid. And the process was EC form. And they scaled that from laboratory to bench scale to pilot scale. Last year, they licensed that technology to OCO to commercialize. Why? Because OCO and its founders have built 18 different green chemical and power companies over the last 35 years. Commercially, we've been very busy over the last year in terms of OCO. We have met with a wide variety of CO2 suppliers and customers in the Pacific Northwest, from coal plants to bioethanol plants. We've talked to almost every electricity generator and Northwest utilities. Why the Northwest? Because, ladies and gentlemen, the Pacific Northwest, and specifically the Columbia Basin, is going to be the cradle of the revolution of the renewable energy industry. We've also contracted and built partnerships with research and development partners, including the Pacific Northwest National Labs, the Montana State University, the University of South Florida, and DNV itself. We have concluded partnerships with a variety of different component manufacturers and engineering service partners so we can build the plants that we need to go build. We've met with Columbia River Basin cities and port authorities, including the Port of Morrow in Boardman, Oregon, which could very well be ground zero for the revolution that we're talking about in terms of converting CO2 into formic acid. And last but not least, we're working with the Department of Energy, who awarded us a $1.8 million development grant to help us commercialize this technology and take it down the next step forward that we won in September with our R&D partners. Our business model is very straightforward. In phase one, we're going to be manufacturing modules. We're going to be building and operating plants that use those modules, making and selling formic acid, and creating lots and lots of new intellectual property along the way at very high profit margins. In phase two, when we have process guarantees that we can extend to large utilities and fossil fuel-based producers, we'll be able to sell those modules and license that IP as well, and expand the market. Financially, our revenue is very simply driven by the number of modules that we have in service. The more modules that we can make, the more that we can deploy, and the price of formic acid, which is about $1,000 a ton today. Our margin drivers are the cost of those modules and the cost of electricity. And the reason, again, that we're based in the Pacific Northwest is because we have the cheapest industrial-rated power in the entire North American continent and practically the world. And you can see the scale ramp that we're on to get there. OCO leadership is made by my father and founder, Terry Brix. He's the gentleman who started 18 green chemicals all within the state of Oregon, Washington, and Montana over the last 35 years with 7 exits and 1 IPO. He's also ex-Battelle. I'm also a chemical engineer and MBA myself, and worked at Chevron Research, starting up 10 different hydroprocessing and hydrotreating facilities in Asia in the 90s. And over the last 20 years, have been running several different multi-billion-dollar businesses at Microsoft Corporation, starting them from 0 and bringing them to $1 to $10 billion in size. Our technology advisory committee consists of 6 PhD chemical and material science engineers who've done and seen everything in the chemical industry, and we're very pleased to have them on board consulting with us in all the major technology areas of development and commercialization that are ahead of us. And a last parting thought, because I'm over time. We can do good and we can make money if we use and don't waste our carbon dioxide. Thank you very much.
Thank you, Todd. Let's have Dan kick us off on this one.
All right. Well, a couple of questions. Let's start off with the business model. Business model in phase 1 that you were mentioning. You guys are going to manufacture these, install them, and basically run them, from what I understand, and then sell the product at a profit. Again, that would be capital intensive, that you have to make them, install them, and not immediate payback. How do you plan on, what kind of cost is that going to incur?
Well, we're extremely capital efficient. So we can generate about $1 million in revenue for $1 million of capital investment at our current cost structure. So each one of those refrigerators I showed, each one of those modules, today runs about $400,000 per unit. Each of those units produce about 1 ton of formic acid today and generate about $1,000 in revenue per day at about a 50 to 60% gross margin, okay? And so, and that is 3 times as capital efficient as the existing formic acid production process. We are very capital efficient. Moreover, over time, because this is a mass-produced, mass-assembled type of product, and it operates at room temperature and pressure, we can mass manufacture these, conceivably even out of injection plastic molding. And when you can start making modules out of plastic, the cost can go down dramatically. And that's why we're very optimistic that in 10 to 15-year time, we'll be able to make this cheaper than diesel or gasoline.
Okay, so at $400,000 a piece, is that the complete unit installed?
Yes, that is the distributed cost of our capital footprint. It's predominantly module-based, but we also have intermediate storage and compressor vehicles and separation vessels, et cetera.
Okay. Can you talk a little bit about your traction with the customers? You've been talking to a lot of customers. Are they committed? What's their, what hesitations do they have? What are they telling you?
Well, the biggest problem is actually we don't have a lot of carbon capture capabilities in this country today. We only have 10 plants that actually capture carbon dioxide out of, say, the flue stack of a natural gas burning plant or a coal plant. And so what we've decided to do is to bootstrap our entire efforts by focusing on industrial production sources that produce 99, almost 100% pure carbon dioxide a day, which is our bioethanol plants. We have 300 bioethanol plants in the United States and Canada alone. They generate 100% pure carbon dioxide that goes straight into the atmosphere today. Each one of them that we've talked to, and we've talked to every single one in the Northwest and even some in the Midwest, will be glad to sell us carbon dioxide from anywhere from $20 to $30 a ton. And we say, thank you very much, we'll turn that into $1,000 a ton. The key thing is the electricity, because we need lots of very cheap, inexpensive, and ideally and preferentially renewable electricity in order to make this not only a carbon neutral process, but a carbon negative process.
Thanks, and can you walk me through how the carbon goes from emission to your facility?
Absolutely. So I'll take the example that we're going to probably first commercialize with, which is a bioethanol plant. So bioethanol plants take corn that's grown typically in the Midwest, it's shipped out to the Northwest, and it's fermented. It's turned into alcohol, ethanol. And as part of that fermentation process, all the little yeasties that process and the sugars eat them up and make the ethanol emit carbon dioxide purely as a byproduct. Today, what a lot of these ethanol plants do is they have a small 12 to 14-inch offtake line from their flue stack that goes to an adjacent co-located plant. So we would build right next to the bioethanol plant. There would be a small pipe running across the fence line into our plant, and we would take all the carbon dioxide that they can produce, so we can turn it into carbon dioxide. And we plan to replicate that model with every single ethanol plant that we can find. And by demonstrating these economics at a bioethanol plant, we expect large utilities and coal burning plants, if there's any left in 10 years, and natural gas burning plants to say, hey, this is a great solution. We now think we can afford to invest in carbon capture technologies because we know we can make a lot more money by using that carbon dioxide to cover the cost of the investment of capturing the carbon dioxide in the first place. And we're talking at the gigaton scale.
Amazing. So your pitch is to set up a plant adjacent to existing plants. Your
Yeah,
customers.
here's the great thing about industry in America today. It's all located in rural areas with lots of land around, and you can just work with your helpful local port commissioner or local economic development authority in a lot of these rural areas who want high-paid manufacturing jobs that don't pollute their environment. And they want companies like that, like OCO, to set up shop in those neighborhoods and take advantage of the natural resources and the environment that they have.
Yeah, it sounds like one of the main challenges, like if I was starting this business, is just the first customer. How do you go from 0 to 1? Because it's hard just to pilot this with a small operation. It's almost like you have to go big or do nothing.
Actually, this is the beautiful part of the process. That has been the death knell of so many different bioproduct-based companies. It's like, well, if we build a really big plant, ultimately we can kind of break even and be less expensive than the fossil thing that we're supposed to be replacing, okay? That model doesn't work for a variety of different reasons we don't have the time to go into now. What does work is modular production and the powers of mass assembly, mass-produced assembly operations. And that's what we're doing. We're saying don't build one big giant module or a refrigerator the size of the Kingdom or something, right? Instead, we're saying make one standard module, make a lot of them in mass-produced, highly robot-assembled type of factories, make them very cheaply, and just hook them up in an array, like server racks. We have data farms all over central Oregon and eastern Washington. This is exactly the way it would kind of work, except instead of only electrons coming in, we'd also bring in some carbon dioxide and water as well, and have formic acid coming out the back rather than a web page being served from Amazon.
What do you think is the critical item to get you over the hump to get one of these installed?
It's a small matter of money, actually, and it's to build, because we've been scaling this up. We need to build a full-scale unit. If we can build one full-scale unit, which we're only 10x away from scaling to, so we've already scaled the process up like 100x. And the Department of Energy grant is going to allow us to scale up another 10x, okay? And then there's one more increment after that we need to do. And then we have our refrigerator, okay? When you have the refrigerator and you can walk into a bank, I think the US bank folks who are around here today talking about this, it's like, hey, show us how your refrigerator produces formic acid and makes a lot of money. You build one, then you go build 10, and then you go build 100, and you build a manufacturing plant, and you build, thousands of these every single month, and you deploy them all through these sites, and all of a sudden, you're capturing tons of carbon dioxide and converting it into formic acid, and you're gradually then starting to disrupt every single petrochemical producer in the country that uses natural gas and oil as a feedstock, and then ultimately you're starting to disrupt gasoline and diesel production as well, because formic acid has a comparable energy content for dollar kilowatt as gasoline does, at a cost of about $300 a ton.
We're going to go to the audience. There's one.
Hi. So your customers, do they see this as a natural problem that they want to solve and make money on, or is it too much work for them to actually even want to go through the hassle of working with you guys and creating another manufacturing plant right next to their facility?
Every single supplier says, hey, as long as you're not disrupting my flue gas stack or my operations, you can take my CO2. That's what every single one has said. And yes, we'll put up the money, the $10,000 it takes to take an offtake of CO2. The CO2 is not the problem from these types of companies. And every customer who consumes formic acid, there's only one plant in the entire Western Hemisphere for making formic acid, and it's a German company based in Louisiana. We think an American company can service the formic acid demand in North America, or should be able to, at least as well as that German company, and service, first of all, the entire Western Hemisphere. And because we have to import so much formic acid from this German company, the market prices in North America are $1,300 a ton, whereas the global average is like $1,000 a ton. So we have lots of profit margin to work with for many, many years before we can start driving down the price and really scaling up the volume.
Is there a final question from the audience? There it is, behind.
Hi, my question is about how do you protect the workers who are working with the product and also the land that the unit is built on against the concentrated fluid?
Safety is job one. This is an acidic product, and in high concentrations, it is not, it's like any kind of acid. It will burn your skin and burn your eyes, okay? And so there are a lot of safety precautions, but the chemical industry is a $2 trillion business in the world today, and every single person in each of those plants operates with a very high safety bar, and that's my job number one. I worked at Chevron in producing refinery facilities, and safety was always job one there, and it'll be job one here. The other thing to keep in mind, though, about formic acid is that if in the event it should be spilled or distributed on the ground, it breaks down back into carbon dioxide and water, okay, within days. And in fact, the Oregon Department of Transportation sprays it on your roads every year to get rid of the ice in the form of potassium formate, okay? Potassium formate is a derivative of formic acid, and it's a salt. It's also used to take off the ice off of wings. And so the Department of Oregon of Transportation thinks it's perfectly good, and it is, to spray it on roads because it helps lower the melting point, right, of ice and melts the roads so you can drive more safely.
Thank you so much. That
Thank
was
you.
a great presentation. Todd Brix, OCO Corporation.